Process industries produce countless types of goods and services. Just as varied are the control methods used during production. Some industrial processes need little control and operate within a wide range of tolerance. Others require much finer control. The degree of control depends on the specific process and is carried out by the controller.
I'm beginning to get the idea how your operation works. Some of your processes are pretty complex.
Yeah, so's our instrumentation. We depend on our control loops to keep those processes smoothly. And the controller is the most important piece of equipment in a loop. It's the brain behind the action.
The controller plays a critical role in any automated process because it's responsible for making the decisions that affect the process variables. However, the controller is only one of several components in a feedback control loop. A control loop is designed to respond to upsets in the process. Upsets are external conditions that change the demand placed on the process. These conditions cause changes in the controlled variable. Information about these changes is gathered by the sensor. The sensor changes this value to a signal, which is sent by the transmitter to the controller. The controller compares the signal to a set point and, based on the deviation, decides if any action needs to be taken. The controller's output signal positions the final control element. The final control element responds to this signal by changing the value of the manipulated variable. The manipulated variable, in turn, affects the value of the controlled variable, which is again detected by the sensor. The cycle is repeated until the value of the controlled variable matches the set point. How this is accomplished, that is, the mode of control action, is a function of the controller. There are 4 modes of control: two-position, proportional, integral, and derivative. Two-position or on-off control is discrete, so that the signal to the final control element is either 0 or 100%. Proportional, integral, and derivative control are continuous modes of control. Controllers may have one or more of these control modes. Let's look at two-position control first. It's the simplest mode. A heating system, for example, might use this type of control. The heating system turns on when the room temperature falls below a set point. When temperature exceeds the set point, the system turns off. In other words, it has 2 positions, on and off. Two-position control is used in industry when only 2 stages of control are needed. A typical industrial two-position control process might use the same operational principles shown in this diagram. Here, liquid in a tank must be kept within a certain temperature range. In addition to the two-position controller, the components in this feedback loop include a sensor, transmitter, and a final control element. The final control element in this diagram is a valve. Changes in temperature are detected by the sensor and transmitted as a signal to the controller. The controller determines that the temperature is below set point and sends an output signal to open the steam valve. The valve opens, sending steam, the manipulated variable, to heat the tank. Feedback is continuous. So when the temperature of the liquid in the tank rises above set point, the cycle is repeated and the steam valve closes. In this example, the control mode is simple: 2 positions, open or closed. This process can also be illustrated graphically. We'll assume that the liquid in the tank is at set point and the valve is closed. The liquid begins to cool and the temperature drops below set point. The controller, responding to the sensor's signal, generates an output signal to open the valve. The temperature, however, continues to drop. Remember that the control loop doesn't act immediately because of the response time of the sensor. Also, it takes some time for the steam to heat the liquid in the tank. The temperature eventually begins to rise. When it's just above the set point, the controller again senses the deviation and closes the valve. Because of response time, the temperature continues to rise slightly before it drops. When it drops just below the set point, the valve opens and the cycle continues. You can see how two-position control causes oscillations in the controlled variable. If oscillations in the controlled variable can be tolerated, two-position control is adequate. If the oscillations can't be tolerated because of the nature of the process, a different control method must be used. Information about two-position control can be found in your workbook. The oscillations that result from two-position control may not be appropriate for some systems. The two positions of the final control element may provide either too much or too little control. Those systems that can't tolerate significant oscillations require proportional control. Proportional action provides continuous control. This means that the final control element can be positioned at any point within its throttling range, not just on or off. Because there's a finer degree of control, oscillations are minimized. Proportional control is often used if the value of the controlled variable changes in response to upsets.
As I said, this records the outlet steam pressure of the boiler. When the boiler pressure reaches 900 psi, a pressure gauge on the header senses that, so the fuel flow to the boiler is reduced. There's a transmitter in the field, same place as the sensor. That's what generates the signal.
So the controller detects a difference between set point and actual pressure. It sends a signal to the control valve. The valve closes, reduces fuel flow, and boiler pressure drops.
You got it.
That example of simple proportional action can be illustrated by this diagram showing control of boiler pressure. Fuel is piped into a boiler where it's used to heat water. The resulting steam is used throughout the plant. Fuel flow is controlled by a valve. Because of the dynamics of the process, two-position control would not keep boiler pressure within tolerable limits. The on-off action of the valve would cause either too much or too little fuel to reach the boiler, causing pressure to fluctuate. Proportional control action helps avoid this problem.
Most of our controllers are proportional because our boilers need a pretty accurate degree of control. We've got to be able to position that equipment any way that's necessary to keep boiler pressure within range. Come on, let's take a look.
When proportional control action is used in this example, the controller receives the signal from the pressure transmitter on the header. The controller responds to any deviation from set point by positioning the final control element, that is, the fuel control valve, in proportion to the deviation. The valve can be in any position, open, closed, or anywhere in between. This allows for more gradual adjustment of fuel flow as the pressure in the boiler changes. Proportional controllers can maintain a continuous relationship between the controlled variable, pressure in this case, and the position of the final control element. If the set point of the outlet pressure is 900 psi, the controller will move the fuel control valve to a position that will help achieve that pressure, and the valve will be continuously repositioned to maintain the desired pressure. This relationship between the value of the controlled variable and the position of the final control element can be shown graphically. When boiler pressure, the controlled variable, is at maximum, less is needed. The valve is nearly closed. Likewise, when pressure is at a minimum, the maximum amount of fuel is needed so the valve is fully open. In other words, it takes a full range of input to produce a full range of valve movement. Any other changes in pressure cause the proportional controller to readjust the position of the fuel control valve proportionally. In most cases, the amount of proportional control action can be adjusted. This adjustment is referred to as changing the width or percentage of the proportional band. Proportional band is defined as the amount of input change needed to provide a full range of output change. It's usually referred to in percentages of input. Changes in proportional control action are also expressed as changes in proportional gain. Proportional gain is the ratio of the change in output to the change in input. In the example we've been using, it takes 100% input to achieve a full range of output. So the proportional band is 100% and the gain is 1. If the proportional action were adjusted so that only half the change in input would be needed to fully open or close the valve, we would achieve the same output with half as much input. Since you need only 50% of the input to achieve full output, the proportional band is 50% and the gain is 2. You can achieve the opposite effect by adjusting the proportional action in the other direction. In this case, a full range of input change results in only a 50% change in output. The result? The same input with half as much output. Since you need twice the input to achieve full output, the proportional band is now 200% and the gain is 5. A wide proportional band or low gain, then, corresponds to a less sensitive response. A narrow proportional band or high gain corresponds to a more sensitive response. Because you may be adjusting the proportional band in various feedback control loops, a sound understanding of proportional action is essential. Your workbook contains information on proportional band and proportional gain. The amount of control action that's needed depends on the process. Each process has its own characteristics and variables. So each process has a specific proportional action within which the process operates efficiently. Extremes in proportional action can be illustrated graphically. When proportional action is excessive, even a relatively small change in set point results in a significant change in output. This can cause an oscillating effect similar to two-position control action. On the other hand, insufficient proportional control action allows virtually no control. A large change in input causes very little change in output. Control action takes place very slowly over a long period of time. Generally, proper control action is somewhere between these two extremes. Oscillation occurs, but not too much. Control is quick, but not so fast that the process fluctuates erratically. However, notice that as the oscillations settle out and the process reaches a steady state, there's a difference between the set point and the value of the controlled variable. This condition is known as offset. Offset is inherent in proportional control systems. To understand offset, think of how you control the speed of a car. Suppose you're driving along a flat road at 45 miles per hour, the speed limit. The position of the accelerator is proper to maintain your speed. Now you begin to climb a hill. Your speed starts to drop. Your response is to apply proportional action. That is, to depress the accelerator an amount proportional to the amount you have slowed, or the error. As you do so, the speed stops dropping and steadies out again. You're now climbing the hill at a constant speed, using more gas. However, you're no longer traveling at 45 miles per hour. You're moving at a slower speed, say 40 miles per hour. This difference is offset. How do you correct for offset? You give the engine a little more gas, recheck your speed, and give it a little more gas if necessary. Then you continue this sequence of adjusting and checking until you've reached 45 miles per hour again. Industrial proportional controllers usually have a second control action to do this checking, adjusting, and rechecking until the controlled variable is back at set point. This is called integral action. Integral action, sometimes referred to as reset action, continues to provide additional control action as long as offset is present. Integral action adjusts the output until the process returns to set point. With integral action, the output called for by proportional action is repeated until the final control element is positioned to correct for offset. Proportional plus integral control is often referred to as PI control. Proportional and integral control can also be combined with derivative or rate control. To understand derivative control, let's go back to the driving example. Suppose you reach the top of the hill and begin to go down a steep grade. As soon as your speed begins to increase, your first action is to remove your foot from the accelerator and apply the brakes. Then, as your speed stabilizes, you begin to carefully apply gas using proportional and integral action to return your speed to the desired value or set point. Your first response was to overcompensate for the rapid change in speed by lifting your foot off the accelerator. This action is similar to derivative control. Derivative control responds to the rate at which the process is deviating from set point. Once the change has stopped, proportional and integral action continue until the set point is reached. Proportional plus integral plus derivative action is called PID control. PID control is useful in processes that are slow to respond and need additional control action. With derivative action, the controller responds more quickly, so the final control element is positioned faster. As a result, overshoot and oscillations are reduced. Technicians and operators who work with control processes should understand how proportional, integral, and derivative control work together to provide an efficient and accurate means of automatic control.
So that boiler we just saw is controlled automatically.
Yeah, any offset is automatically corrected by integral control action. Like fuel flow to the boilers. When there's a change in demand in the system, the control valve's going to wind up in a position that either lets in too much or too little fuel. So integral control action repositions the valve to compensate for that offset.
Derivative control has to do with speed, right? How fast the controller responds.
Yes, derivative action would reposition a final control element, like a valve in this case, more quickly. If it weren't for any derivative control, the pressure would be constantly changing. The valve would be constantly repositioning, causing a lot of wear and tear on the equipment. So in our operation, like in most industries, I guess, we need all three types of control. That is, proportional, integral, and derivative.
In this videotape, we've seen 4 modes of control used in industrial processes. Each has characteristics that determine how effectively it will work in manufacturing operations. Two-position or on-off control responds only to the presence of an error or deviation. It's a relatively inexpensive and simple control mode. Two-position control action often results in oscillations in the value of the controlled variable. Two-position control is useful in applications where the process does not need a fine degree of control and can tolerate these oscillations. More precise control can be obtained through proportional control action. Proportional control action provides continuous control by responding directly to the magnitude of the error or deviation. A proportional control mode that does not include either integral or derivative action is a relatively simple type of control. It is inherently stable when the controller is properly tuned. That is, when it is adjusted to work within the process it is controlling. Proportional control alone is also relatively easy to tune, as compared with PI or PID control. When offset occurs in a proportional control mode, the offset occurs at a steady rate. Remember that offset is inherent in proportional control modes and must be corrected. Like two-position control, proportional control can be applied to processes that do not need precise control. For example, when liquid level in a tank does not need to be maintained at a critical level. Integral or reset action is often combined with proportional action to correct for the offset that's inherent in all proportional control. Integral action responds to the duration of the error. Proportional plus integral, or PI control action, corrects offset by bringing the actual value of the variable back to the set point after an upset has occurred. Proportional plus integral control has a somewhat faster response than proportional action alone, although not as fast as PID control. With integral control, there is a lag time before offset is corrected. In some cases, this results in instability in the process loop. One exception to this is flow control. Flow control loops are very fast and often noisy. Integral control action is often added to the feedback controller in these loops to provide a dampening or filtering action for the loop. Derivative or rate action may be combined with proportional and integral action to compensate for processes that have a slow response. Derivative action responds to how rapidly the process is deviating from set point. Proportional plus integral plus derivative, PID control, is the most complex of the control modes discussed so far. A PID controller responds rapidly to upsets in the process with less lag time and prevents overshoot in output. PID controllers are difficult to tune because there are 3 separate adjustments that must be made. However, the more accurately they are tuned, the more precise the control of the process. PID controllers are more common in processes where temperature is the controlled variable, because the response times of these processes are relatively slow. PID controllers are rarely found in flow control, because the process itself responds so quickly that any derivative action would overcompensate for the upset. This overview of the types of control modes will help you apply control theory to the processes in your facility. Remember, however, that designs and operational principles differ, so always follow the manufacturer's instructions and your facility's guidelines before working on any control instruments.